This information is presented by Bluewater Auto Restoration. Welcome back. This is week 19 of the 2026 Bluewater Auto Restoration podcast. We release new podcasts every Saturday morning. In this deep dive, we look at Eskaz Brżovka Strakamise, a history of Czech engineering excellence.
Thanks for having me back.
So I want you to imagine for a second that you are looking at this lightweight, brightly colored dirt bike, right? And it's flying 60 feet through the air on a motocross track.
Oh, yeah, totally.
The rider lands, whips around a berm, and then accelerates with this ear-splitting, high-pitched scream. Now, imagine realizing that the DNA of that very specific recreational machine, it traces directly back to the design and manufacture of lethal post-World War I automatic weapons.
It's a massive contradiction, isn't it?
Exactly. I mean, we tend to look at high-performance vehicles and just assume their creators have, always been obsessed with speed. But today, we're exploring a company that completely shatters that assumption. We are tracking a century of stubborn, almost unbelievable engineering resilience.
Yeah, a company that started out making firearms, completely pivoted to building bicycles just to survive a global economic crash, and somehow ended up dominating global motorcycle racing.
And fundamentally revolutionizing the physics of off-road engines. So for anyone listening right now who wonders how military precision actually translates into consumer machinery, well, you are in for a wild ride today.
It is arguably one of the most remarkable and frankly improbable industrial arcs of the 20th century.
Yeah.
To really grasp the magnitude of this evolution, we have to ground ourselves in the geographic and historical reality of the time.
All right, set the stage for us.
We are starting our journey in September 1919. The location is the town of Strakanec in what was then the newly formed nation of Czechoslovakia, the entity that would eventually become known to the entire world simply as Z began its life as a branch of the massive Akota Works armament.
Akota Works, wow.
Right. And think about the geopolitical landscape here. The First World War has just ended. The Austro-Hungarian Empire has violently collapsed. In the middle of this massive, chaotic shifting of borders, you have a factory established with one extremely serious mandate, which is manufacturing weapons.
Yeah.
So our story of engineering resilience begins quite literally in the crucible of post-war arms production.
Starting off as an arms manufacturer called, and I'm going to try to pronounce this right, Česká Zbrojovka.
Nailed it.
Thanks. The South Bohemian Armament Works, it sets a very specific tone. By 1922, they are absorbing other plants in Veszprady in Prague. They are highly successful, churning out pistols, air guns, and automatic weapons. Their entire corporate identity is firepower.
Oh, entirely.
But then the timeline hits 1929. The global economy just goes into a catastrophic tailspin with the Great Depression. The post-war appetite for weapons it evaporates. Governments are broke, so military contracts vanish.
They're gone overnight.
Exactly. So to survive, this hardcore weapons manufacturer does something that sounds totally absurd on paper. They buy a bicycle parts plant in Kralupy nad Vltavou, and they start making bicycles.
Yep. Bicycles.
And they don't just tinker with it. They start exporting these bicycles globally to Europe, Asia, Africa, and South America. By 1932, they're strapping small motors onto these bicycles. And by 1935, they launch their very first true ground-up motorcycle.
That's an insane timeline.
They become Czechoslovakia's largest motorcycle manufacturer almost overnight.
Okay, let's unpack this. I'm trying to wrap my head around this. Is this basically like Percy Spencer realizing his military radar magnetron could melt a chocolate bar and suddenly we have consumer microwaves?
That's a really good way to look at it, actually.
Did they just take military specifications and aim them blindly at civilians? Because jumping from automatic pistols to a global bicycle export empire in 3 years seems insanely risky. If no one is buying guns, why didn't they just, board up the windows and lay off the workers until the economy recovered? That is the logical assumption, right?
Yep.
But you have to look at the physical reality of a 1920s arms factory. You can't just hit the pause button on a massive industrial complex.
Because of the overhead.
Exactly. You have floors full of incredibly expensive machinery. We're talking heavy-duty lathes, stamping presses, milling machines. More importantly, you have an entire workforce of metallurgists and machinists who are highly trained in exact microscopic tolerances.
Right. Highly specialized labor.
Yeah. If you board up the windows, that equipment rusts, the workers leave to find food, and the company dies permanently. Now, consider the sheer mechanics of an automatic firearm.
Okay.
It requires absolute, unyielding precision. The metallurgy has to withstand repeated, contained explosions. If a single internal part is off by a fraction of a millimeter, the weapon jams, and in a combat scenario, someone loses their life.
The stakes couldn't be higher.
Precisely. So when the arms market collapsed, the leadership of Strategies looked at their assets and realized their actual product wasn't guns. Their product was the mass production of hyper-precise metal components.
Oh, that is a massive paradigm shift. They weren't a gun company, they were a precision metal company.
Exactly. And that ethos of precision transfers directly to the bicycle. They didn't build flimsy, disposable consumer goods. They built bicycles engineered by gunsmiths.
That sounds indestructible.
They were. The bearings, the gears, the frame welds, everything was subjected to arms-grade quality control. These bicycles were virtually indestructible because they already had a massive, hyper-efficient production line set up for weapons. They could manufacture these high-quality bicycles at a scale and speed that terrified their competitors.
Wow.
Yeah, and this massive volume allowed them to flood the export market, keeping the factory lights on and the workers fed. So when they transitioned to motorized bicycles in 1932 and then built a bespoke motorcycle in 1935, they were applying that exact same philosophy. The machine must not fail, it must be easily maintained in the field, and the parts must fit together with flawless, military-grade precision.
So they took the existential survival instinct of the entire company and literally welded it into the frames of these early bikes.
That's a great way to put it.
And that trial and error period of the early 30s, figuring out how to mount an engine to a bicycle frame without the vibration tearing the metal apart, it culminated incredibly fast. Just 1 year after their first true motorcycle, they released what many consider their pre-war masterpiece. Let's dig into the 1936 Z175 standard.
Yeah, the 175 standard is the definitive milestone. What's fascinating here is that this is the moment Z firmly stopped being a company that put motors on bicycles and became a fully realized, dedicated motorcycle manufacturer. It is a masterclass in pre-war utilitarian engineering.
I really want to paint a clear visual of this machine for you listening because it doesn't look like anything on the road today. It has a very distinctive, narrow teardrop fuel tank.
Very iconic.
And when you look at the front suspension, you don't see those shiny sliding telescopic tubes we have on modern bikes. You see a pressed steel girder fork. It's a parallelogram design made of thick steel. The frame itself isn't just welded steel tubes. It is a double riveted and bolted steel frame.
It looks heavy.
Yeah, seeing rivets on a motorcycle frame feels like you're looking at a steam locomotive or a bridge, not a vehicle. It rolls on these very tall, thin 19-inch wire spoke wheels. And the steering mechanism is wild. It has a manual friction steering damper. You literally turn a giant knob near the handlebars that physically squeezes friction discs together to stiffen up how the handlebars turn.
That girder fork and riveted frame are direct descendants of their industrial capabilities. I mean, telescopic forks were in their infancy then and often leaked or bent under stress.
Right.
A pressed steel girder fork moving on mechanical pivots was incredibly strong. It could take immense abuse. But the true heart of this machine was the engine. It was a 172.5 cc two-stroke single-cylinder monoblock.
Okay, let's break that down.
Sure. Let's look at the geometry of that cylinder. It had a 60-millimeter bore, that's the width of the cylinder, and a 61-millimeter stroke, which is how far the piston travels up and down.
Wait, I see the term undersquare used for engines where the stroke is longer than the bore. Why does that matter? Does it change how the bike actually rides?
It changes everything about how the power is delivered. Think of the stroke like the crank arm on a bicycle pedal.
Okay.
If you're a very long crank arm, you get a lot of leverage to push a heavy gear uphill, but you can't spin your legs very fast. If the crank arm is short, you have less leverage, but you can spin your legs at a blistering speed.
Oh, that makes total sense.
Right. An undersquare engine with that longer stroke provides tremendous mechanical leverage on the crankshaft. It generates strong, steady torque at very low RPMs. It's not going to rev fast or win drag races, but it will pull you through thick mud or up a steep cobblestone hill without stalling.
So leverage over speed?
Precisely. And they paired that undersquare design with a very low compression ratio of 5.9 to 1.
Which is really low, right?
Very low. Compression ratio is simply how tightly the fuel and air mixture is squeezed inside the cylinder before the spark plug ignites it. Modern performance bikes might have compression ratios of 13 to 1 or higher.
I'm assuming that low compression was a deliberate choice for the environment they were operating in. Because in 1936 Europe, you aren't pulling up to a pristine gas station with high-octane premium fuel. You're probably buying fuel out of a barrel at a general store.
Exactly. Fuel quality in the 1930s was wildly inconsistent, especially in rural areas. If you run low-octane, low-quality fuel in a high-compression engine, the mixture will explode prematurely under pressure before the spark plug even fires.
That sounds bad.
It's terrible. That's called engine knock or pre-detonation,
Yeah.
and it will physically destroy the piston. By keeping the compression ratio at 5.9 to 1, the Z engineers ensured that this motorcycle could run on absolute garbage fuel. It might not be efficient, but it would not blow up.
It's idiot-proof engineering. Now, this engine produced about 6.4 horsepower at 4,000 RPM. I look at that number and I think about my modern riding lawnmower that has double that horsepower. It sounds almost comically underpowered.
It sounds minimal today, sure, but you have to look at the broader mechanical system. This engine featured an aluminum alloy piston with a deflector built into the top.
A deflector?
Yeah. In early two-strokes, you didn't have complex exhaust and intake valves. The fresh fuel and air come in, and the exhaust goes out through holes or ports in the side of the cylinder wall. The deflector was a physical hump on top of the piston that directed the incoming fresh fuel upward into the cylinder head, pushing the burnt exhaust gases out the other side without the two mixing too much.
Oh, okay.
It's called cross-flow scavenging. It was simple, mechanically robust, and required zero moving valvetrain parts. They also used a Bosch 15W flywheel magneto ignition system.
I've always heard that a magneto is brilliant for older machines. I know a modern bike needs a heavy lead-acid battery to send electricity to a coil to create a spark. But a magneto generates its own spark just by the engine turning, right?
That's exactly right. A magneto is essentially a small electrical generator driven directly by the spinning of the engine's crankshaft. It uses permanent magnets moving past a coil of wire to create the electrical pulse for the spark plug.
And why is that brilliant for 1936?
Because batteries from that era were heavy, they leaked corrosive acid, they failed in extreme temperatures, and they constantly needed charging. With a magneto, as long as the engine is turning, you have spark. You could park the bike in a freezing barn for a year, kick the starter, and it would generate its own electricity instantly.
So no dead batteries to leave you stranded in the middle of nowhere. Now, transferring that 6.4 horsepower to the wheel was a 3-speed gearbox. And this is where the physical reality of riding this machine becomes fascinating. The shifter wasn't a foot pedal. It was a hand lever mounted directly to the side of the fuel tank.
Yeah, imagine that.
You are bumping along an unpaved road, holding on for dear life, and to change gears, you have to completely take one hand off the handlebars and physically row a lever next to your knee. Plus, the rider had to mix their own oil and fuel at a 1:25 ratio directly in that teardrop tank. You are your own oil pump. The top speed was around 85 kilometers per hour, which is about 52 miles per hour.
And realistically, you wouldn't want to go much faster than that. That 6.4 horsepower was meant to move a machine that weighed only 97 kilograms, about 213 pounds.
That's incredibly light.
It was. It was designed to sip fuel at a rate of roughly 3 liters per 100 kilometers. But when you talk about the physical reality of riding, we have to talk about the chassis. It had a rigid rear suspension.
Ouch.
Yeah. That means the rear wheel was bolted directly to the steel frame. There were no shock absorbers, no springs. The only cushion between the rider's spine and the road was the air inside the 19-inch tire and a pair of heavy coil springs mounted directly underneath the leather saddle.
I really want to put myself in the saddle of this thing. You've got a rigid rear frame transferring every impact directly to the seat. You've got a manual friction steering damper that you have to crank down so the front wheel doesn't wobble. You're riding on 1930s dirt roads, gravel paths, and rutted cobblestones. You're managing a hand shifter, adjusting a spark advance, and feeling every single pebble on the road. It sounds absolutely punishing to ride.
Visceral is the word. You felt the mechanical heartbeat of the machine, the vibration of the underscore engine, the clatter of the girder fork. But look at it through the lens of a former arms manufacturer trying to build civilian transport.
Okay, let's think like a gunsmith.
A rigid rear frame means there are 0 pivot points to wear out. There are no swing arm bearings to collect grit and seize up. There are no hydraulic rear shocks to blow seals and leak fluid.
That makes a lot of sense.
Right. A hand shifter mounted directly to the transmission means you have a simple, direct linkage, rather than a highly complex, delicate ratcheting foot shift mechanism. It was designed so that a rural doctor, a farmer, or a factory worker could maintain it with a basic wrench.
It wasn't designed for comfort. It was designed for certainty. It was freedom. It provided reliable, accessible transport in an increasingly volatile 1936 Europe.
Exactly. And it is precisely this heavy-duty, over-engineered simplicity that riveted steel, the lack of delicate suspension linkages, the robust magneto that allows these machines to still exist. If they had been built with fragile, overly complex systems, they would have rusted into dust decades ago.
That's a great point.
But because they were built like tanks by people who understood durable manufacturing, we still have them nearly a century later. which leads us to the philosophy of how we handle these incredible survivors today.
Right. That brings us to right now, March 2026, because there is a very specific ongoing restoration project of an early production, circa 1936 Z175, happening at Bluewater Auto Restoration. And this isn't just a matter of slapping on some fresh paint and making it look pretty.
Yeah.
We are talking about the hardcore philosophy of historical preservation.
Oh, absolutely.
Picture this machine as it sits on the workbench right now. It is a stripped-down, time-worn chassis. The original paint is mostly gone, replaced by the deep patina of decades of exposure, but the core materials, that thick steel, the heavy rivets, the girder fork, they still carry the physical history of the Strathconnys factory.
The methodology being applied to this specific 1936 D175 is incredibly rigorous. It begins with exhaustive documentation. Before a single bolt is turned or a component is removed, the entire machine is evaluated, measured, and cataloged.
Like a crime scene.
Very much so. The preservationists study whatever original finishes remain down to a microscopic level. They examine the mounting points and the tool marks to understand exactly how the factory line workers assembled it.
I understand they're deeply focused on the discipline of metalwork. The prime directive is preserving the original material wherever physically possible. If a fender is dented or a frame tab is bent, the instinct isn't to throw it in the scrap bin and order a shiny, modern replica part.
No, never.
The instinct is to carefully heat, reshape, and repair the original 1936 steel. They are actively sourcing a proper 172cc monoblock engine and original hardware to ensure the soul of the bike remains entirely intact. The final finish will involve traditional black paintwork, period-correct chemical coatings, and hand-applied detailing.
That's the way it should be done.
But I want to play devil's advocate here. If the entire goal of the Yeezy engineers in 1936 was to create the ultimate, reliable, practical, everyday transport, well, wouldn't upgrading some of these components actually honor their intention better?
Okay, where are you going with this?
For example, those old mechanical drum brakes. Drum brakes work by having brake shoes push outward against the inside of a metal cylinder, right? And when they get hot from friction, that outer drum expands, moving away from the shoes, which causes terrifying brake fade.
Yes, that is a known issue.
So if we know the original 125mm mechanical drum brakes fade and can barely stop the bike in modern traffic, why keep them? Why not hide a modern hydraulic disc brake in there to make it safe and reliable for today?
You've just hit on one of the most intense, ongoing philosophical debates in the restoration world. It's the ship of Theseus paradox applied to vintage machinery. Do you restore the spirit of the machine as a daily rider, or do you preserve the historical record?
Right.
The team at Bluewater Auto Restoration is firmly anchored in historical preservation. If you retrofit a modern electronic ignition or hydraulic disc brakes onto a 1936 Z, you are actively erasing the engineering reality of 1936. You are masking the very real challenges that a writer in that era faced.
You're saying the flaws are a critical part of the historical document.
Exactly, though they aren't even flaws. They are realities of the technology of the time. The 125mm drum brake fading tells a specific story about the speed limits, the weight of the bike, and the sparse traffic density of the 1930s. The magneto ignition tells a story about the state of electrical infrastructure.
I hadn't thought about it like that.
Yeah, preservation isn't about making a vehicle convenient for a 21st century rider. It is about maintaining the factory DNA so that future generations can physically touch the solutions that the Strathconnys engineers devised with the tools they had. And this authenticity is crucial because we have to remember the context of 1936. Shortly after this motorcycle rolled off the assembly line, that factory was seized. The world went to war, and the era that allowed this motorcycle to be built vanished completely. Preserving it exactly as it was built is preserving a fleeting, specific moment in history.
That gives me chills. When you look at that riveted frame, you aren't just looking at metal, you are holding a snapshot of a doomed era. Because the world did change overnight. World War II erupts, the factory falls under German occupation, and in a tragic twist of irony, the plant is forcibly converted right back into manufacturing war materials.
A full circle back to their origins.
Yeah. All of that brilliant civilian engineering is abruptly halted. But then the war finally ends. We reach 1946. Czechoslovakia falls under a new, post-war political situation, heavily influenced by the Soviet Union. The company is nationalized. And because of this new Iron Curtain reality and shifting state priorities, firearms production at the Strathconnys plant is permanently shut down.
It's a massive permanent shift. The
Yeah.
company that literally birthed itself through the manufacture of weapons is now entirely out of the firearms business. If we connect this to the bigger picture, the state dictates that Z will focus exclusively on two wheels.
A complete 180.
Yeah. And so they take all of that pent-up industrial capacity, all those precision machines, and aim them squarely at motorcycles. During this post-war period, they explode in scale, becoming the second largest motorcycle manufacturer in all of Europe. They even forge a strategic partnership with BWAR, the other legendary Czech motorcycle brand, to share technologies and consolidate production.
And out of this heavily planned, state-run economy comes a machine that looks so completely alien compared to the rugged, heavy-duty 1936 standard. I'm talking about the 1957 Z501 Azetta scooter and its successor, the 502.
Oh, there's Ela.
If you are listening to this, please pause and search for a picture of a Azetta scooter later. It is a visual trip. The design is dominated by this massive, elongated, torpedo-like front end. Instead of a slender steering column, they built a massive luggage compartment directly over the front wheel. The headlight is deeply recessed into the front of this nose, and there is a flat luggage rack sitting right on top of it. It looks like something out of the Jetsons. It was affectionately, or perhaps practically, dubbed the Eastern Vespa.
The styling is iconic, but the engineering logic behind it was dictated entirely by the socioeconomic reality of the Eastern Bloc. State-run economies didn't prioritize luxury automobiles for the working class. The mandate was to mobilize the masses with cheap, highly reliable, weather-protecting transportation.
Right, getting people to work.
Exactly. A scooter is ideal because the leg shields protect the rider from mud and rain, which is vital if it's your only way to get to the factory all year round. The Azetta fulfilled this utilitarian mandate perfectly. But what is extraordinary is that they delivered a purely practical vehicle wrapped in incredibly avant-garde aerodynamic styling.
The design is brilliant, but I'm trying to figure out the physics of it. Let's look at the spatial packaging. By putting the fuel tank and the luggage space entirely out front over the front wheel, they freed up a massive amount of seating room for the rider and a passenger.
That's true.
But doesn't that completely mess up the center of gravity? If I load a bunch of groceries over the front wheel and the fuel tank is sloshing around up there, how on earth does the steering linkage work? Doesn't the steering become incredibly heavy?
That is exactly the engineering challenge they had to solve. On a traditional scooter, like an Italian Vespa, the engine and the fuel tank are usually packed tightly under the seat or toward the rear, giving you a very light front end that is easy to steer but can be unstable at high speeds.
Makes sense.
The Z engineers decided to flip that dynamic. By pushing the fuel tank forward into that torpedo nose, they intentionally weighted the front wheel. This actually improved traction and high-speed stability on rough roads. But to your point about the steering, because that massive nose is fixed to the frame, they had to design a complex steering linkage inside it. The handlebars pivot, and a system of rods transfers that motion down to the front wheel fork, which pivots independently of the massive bodywork above it.
Wait, so the giant torpedo nose doesn't turn when you turn the handlebar?
Exactly. The body remains stationary while the wheel turns underneath it. It is a radical spatial solution.
Here's where it gets really interesting. Putting the trunk over the front wheel and burying the headlight, that's like the modern EV frunk, but they were doing it in 1957, it's brilliantly weird.
They were looking for dead space and deciding it was the perfect place to put your potatoes. The Azetta was a triumph of practical mobilization. It gave millions of people independence. But while they were churning out these reliable, heavy-duty scooters for everyday commuting, the engineers locked in the back rooms at Streckenese were fundamentally restless.
They were getting bored.
They were. They didn't want to just build practical commuters. The scooter mobilized the masses, but engineers inherently want to push limits. You can't put that genie back in the collar. They wanted pure, unadulterated speed. They wanted to go Grand Prix racing.
It's a psychological phenomenon you see in many pragmatic industries. A company built on rugged simplicity decides to throw its hat into the most technically demanding, glamorous, and expensive arena on earth, Grand Prix motorcycle road racing.
Totally.
Their first major foray was in 1955. They built a 125cc four-stroke single-cylinder engine that put out 14.5 horsepower. It was light, punchy, and it actually managed to take second place at the Swedish Grand Prix.
A great start.
Then, in 1964, they developed a 125cc two-cylinder machine, modeled a bit after a Jawa design. It utilized a double-cradle tubular chassis.
Let me stop you there to explain why that chassis is important. Earlier, we talked about riveted steel and pressed metal. A double cradle tubular chassis uses two continuous steel tubes that run down from the steering head, cradle the engine underneath like a hammock, and swoop back up.
Like a hammock, okay.
Yeah, and it is incredibly stiff. When you are leaning into a high-speed corner, the centrifugal forces try to twist the frame of the motorcycle like a wet towel. A double cradle chassis resists that torsional flex, keeping the wheels perfectly aligned.
So they are learning how to handle higher speeds and tighter corners. That 1964 twin-cylinder put out 24 horsepower and could hit over 115 miles per hour. But the reality of Grand Prix racing is brutal. By the time they perfected it and got it on the track, the competition from Italy and Japan had already moved on. The bike was fundamentally outdated on arrival.
It's a harsh reality.
But instead of giving up, they went completely mad. They went back to the drawing board and birthed an absolute monster. The 1969 to 1970 a Z350 V4 Type 860, engineered by a genius named František Pudil.
The Type 860 V4 is, without a doubt, one of the most astonishing pieces of pure mechanical audacity in the history of motorcycling. Let's really break down what they built. We are talking about an engine with a total displacement of 350 cubic centimeters.
That's tiny.
It is roughly the size of two large coffee mugs. But they divided that tiny volume into four microscopic cylinders arranged in a 90-degree V configuration.
Wait, why a 90-degree V? Why not just put all four cylinders in a straight line across the frame?
Good question. A straight inline-four engine is wide. It sticks out on the sides, which means when you lean the bike over in a corner, the engine cases might scrape the ground. By folding the engine into a V shape, you make it incredibly narrow, allowing for extreme lean angles.
Ah, for cornering clearance.
Yes. And a 90-degree angle specifically provides perfect primary balance, meaning the vibration of the pistons moving up and down naturally cancels each other out, allowing the engine to rev much, much higher without shaking itself to pieces.
So,
And it needed to rev. This was a four-stroke engine featuring two-shaft overhead gear distribution and 4 valves per cylinder.
4 valves per cylinder in 1969 inside an engine where the cylinders are already that tiny.
Yes. Most engines of the era used 2 valves per cylinder, one to let fuel in, one to let exhaust out. But smaller valves are lighter, so they can open and close much faster before the valve springs lose control. 4 tiny valves allow massive airflow at insane RPMs.
The machining on that must have been incredible.
The precision required to machine these miniature valves, the tiny camshafts, and the intricate gears driving them is mind-boggling. This is where you see the ghost of the armaments factory. That heritage of microscopic precision was brought to bear on this engine. Because the internal components were so light and perfectly balanced, this 350cc engine could rev to an astonishing 13,500 RPM. It produced 58 horsepower.
That's a huge jump.
Later versions were pushed to 63 horsepower and could reach speeds of 240 kilometers per hour. That is roughly 150 miles per hour.
150 miles per hour on a motorcycle that weighed barely 300 pounds. It must have sounded like a tearing sheet of metal mixed with a jet turbine. But here's the specification that completely melts my brain to manage that power. It was equipped with an 8-speed gearbox. 8 gears on a motorcycle.
It's wild.
I can barely manage 6 on a modern bike. I'm trying to imagine the rider constantly tap dancing on the shifter just to keep that V4 engine in its power band. Wasn't that incredibly demanding to ride?
To understand why an 8-speed gearbox was mandatory, we have to look at valve timing and power bands. For an engine to produce peak power at 13,500 RPM, it needs massive amounts of fuel and air moving through it very quickly. To achieve this, engineers use something called valve overlap, a moment where both the intake and exhaust valves are open at the same time.
Both at the same time.
Yes. At 13,000 RPM, the sheer velocity of the exiting exhaust gas creates a vacuum that powerfully sucks the fresh intake charge into the cylinder. It works beautifully at high speeds. But at low RPMs, that same valve overlap is disastrous. The fresh fuel simply falls straight through the open exhaust valve. The engine essentially suffocates itself.
Ah, so at low RPMs, it produces almost zero power. It's a peaky engine.
Exactly. The engine might only produce usable power between 11,000 and 13,500 RPM. That is an incredibly narrow window or power band. If the engine speed drops below 11,000 RPM, the bike bogs down and you lose the race.
That is razor thin.
The 8-speed gearbox allowed the rider to keep the engine spinning exactly in that microscopic sweet spot. But the mental and physical load on the rider was immense. You are hurtling toward a corner at 150 miles per hour, braking on the edge of tire grip. You had to rapidly tap dance down through 4 or 5 gears in a split second, matching the engine revs perfectly just to drive out of the corner without stalling. It was a high-wire act.
And despite how incredibly difficult it was to ride, they actually got results. Rider Bohumil Stasa wrestled this V4 to a second-place finish behind the legendary Jarno Saarinen at the 1971 Czechoslovakian Grand Prix.
Quite an achievement.
And even more impressively, at the 1972 Austrian GP, Stasa was actually leading Giacomo Agostini. Agostini was riding for MV Agusta, the undisputed kings of the sport. The Z was leading the mightiest team in the world until a mechanical failure forced a retirement just laps from the end. They proved they could run toe-to-toe with the giants.
They absolutely proved their engineering genius. But that mechanical retirement highlights the fatal flaw of the project. The V4 was essentially a watchmaker's engine. It was immensely complex, comprising hundreds of tiny, highly stressed moving parts spinning at 13,500 RPM.
That sounds fragile.
It was incredibly expensive to manufacture, and it required a massive budget to maintain and constantly rebuild. The economic reality of the Eastern Bloc simply could not support a bottomless development war with Western racing factories. The budget wasn't there. So in 1972, faced with mounting costs, EZ made a stunning, purely pragmatic decision. They abruptly abandoned Grand Prix road racing altogether.
Oh, just walked away.
They packed up the magnificent V4 and walked away. But they took all of that intense engineering talent and directed it toward an arena that was cheaper, dirtier, and ultimately far more suited to their heritage.
So they realize Grand Prix tarmac racing is bleeding them dry. But they still have this massive engineering hunger. Where do you put that energy when you can't afford tarmac? You take it to the dirt. And they didn't just participate, they ruled. If Grand Prix racing was a delicate high-wire act, motocross was a muddy bar brawl, and EZ brought a sledgehammer.
They really did.
They won an unbelievable 7 world championships in the 1960s, and they absolutely dominated the international 6-day trials, the ISDT, which is basically the brutal multi-day Olympics of off-road endurance riding. They won it consistently from 1947 all the way to 1982.
The watershed moment for the global dominance occurred in 1963. At that time, the absolute premier class of motocross was the 500cc division. Conventional wisdom dictated that to race in deep mud and loose dirt, you needed a massive, booming 500cc four-stroke engine to generate the sheer, tractor-like torque required to find traction. Heavy bikes, heavy engines.
Right.
But the Z factory rider, Vlastimil Vasic, showed up at the Czechoslovakian GP on a machine that looked like a toy compared to the competition. He was riding a bored-out 263cc two-stroke single. It was barely half the engine displacement of the 4 strokes he was lining up against.
And he didn't just compete, he beat them all. He won the race against a full grid of 500cc 4-strokes. It was the very first time in history that a 2-stroke had won the Premier Division. That must have absolutely sent shockwaves through the paddock. Everyone must have been staring at this little bike, trying to figure out how it was possible.
It completely upended the physics of the sport. To understand why, we have to look at the fundamental difference between a 2-stroke and a 4-stroke engine.
Okay, lay it on me.
A 4-stroke engine, like the one in your car, requires 4 movements of the piston to make power: intake, compression, power, and exhaust. It only fires every other revolution of the crankshaft. Furthermore, it requires a heavy cylinder head full of valves, camshafts, and a pressurized oiling system.
Lots of moving parts.
A 2-stroke engine fires on every single revolution of the crankshaft. It doesn't have a complex valve train. The piston itself uncovers holes in the cylinder wall to let gases in and out. Because it fires twice as often and lacks all that heavy valvetrain metal, a 2-stroke generates massive power while weighing significantly less. Valic's bike had an unbelievable power-to-weight ratio. But the real secret weapon, the technological leap that EZ introduced to the world, was the expansion chamber exhaust.
I always thought an exhaust pipe was just a dumb metal chimney designed to vent hot gas away from the rider's leg. But you're telling me they essentially turned a hollow metal tube into a mechanical supercharger. How does empty space force fuel into an engine?
It is an absolute masterpiece of fluid dynamics and acoustic engineering. In a 2-stroke engine, because there are no valves, there's the specific fraction of a second when both the intake port letting fresh fuel in and the exhaust port letting burnt gas out are open simultaneously.
Similar to the valve overlap we talked about.
Exactly. The momentum of the fresh pressurized fuel rushing into the cylinder actually pushes the burned exhaust gas out. The problem is that fresh fuel has so much momentum that a significant portion of it shoots straight out the open exhaust port before the piston can rise up and block the hole.
So you are literally throwing unburnt horsepower out the tailpipe. It's incredibly inefficient.
Right. So the C engineers manipulated the physics of sound waves to solve it. They designed an exhaust pipe that isn't just a straight tube. It starts narrow, flares out into a wide, fat cone, the expansion chamber, and then tapers back down into a narrow exit. When the spark plug fires and the hot exhaust gas explodes out of the cylinder, it creates a massive high-speed positive sound wave, a pressure wave traveling down the pipe.
Okay, I'm following.
When that sonic wave hits the diverging cone, the part where the pipe suddenly gets wider, the sudden expansion of volume creates a negative pressure wave, a suction wave, that travels backward toward the engine. This suction actually helps pull the rest of the burnt exhaust gases out of the cylinder, making room for more fresh fuel.
Okay, so the wide part of the pipe literally sucks the exhaust out faster?
Yes, but here is the magic trick. Remember that initial positive pressure wave? It keeps traveling down the pipe until it hits the converging cone, the part where the pipe tapers back down near the rear. When the wave hits that narrowing wall, it bounces off.
It bounces.
It reflects backward, traveling upstream against the flow of the exhaust gas, straight back toward the engine. The engineers precisely calculated the length and angles of these cones based on the temperature and speed of sound. They timed it so perfectly that just as that unburnt fresh fuel is about to spill out of the open exhaust port, this massive reverse pressure wave arrives and violently slams the fresh fuel back into the cylinder right before the piston slams shut.
That is mind-blowing. So they basically turned the exhaust pipe into an invisible, sound wave-powered supercharger. And it worked so effectively that by 1973, their CZ250 motocross bike, the one with the highly distinctive angular aluminum coffin tank, became the absolute ultimate status symbol in early 1970s American motocross. If you were lining up at a dirt track in California or Ohio in 1973 and you were serious about winning, you wanted a Z. But this raises an important question. If they were this dominant and their tech was this revolutionary, how did they not become the biggest dirt bike company on earth today?
This raises an important question, doesn't it? It's the classic ruthless reality of industrial economics. Pioneering a revolutionary technology does not guarantee you get to own the market forever. In fact, being the pioneer often paints a target on your back.
Like putting a bullseye on the coffin tank.
Exactly. The mid-1970s marked the rapid decline of the Yeezy motorcycle brand, and it is drenched in historical irony. The massive industrial powers in Japan, Honda, Yamaha, Suzuki, Kawasaki, were watching Z very closely. They saw the expansion chamber, they saw lightweight two-stroke philosophy, and they realized it was the future.
The turning point hits in 1973, literally the exact same year the Z coffin tank was the king of the hill. Honda releases the Elsinore 250.
Precisely. The Japanese manufacturers took the blueprints of the two-stroke motocross bike and applied their immense, heavily funded, highly automated mass production techniques to it.
Right, they industrialized it.
Yeah, and the state-run Z factory in Czechoslovakia was still relying heavily on older manufacturing techniques and limited state budgets. The Honda Elsinore, by contrast, utilized advanced, lightweight metallurgy, flawless plastics, and highly refined suspension components. More importantly, the Japanese factories continuously innovated at a blistering pace, releasing radically updated models every single year.
And Z couldn't keep up.
The Strakantis factory simply could not match that financial cadence. Inexpensive, hyper-reliable, technically advanced Japanese motorcycles flooded the global market. They ironed out the quirks of the two-stroke engine, perfected the expansion chamber that Z had invented, and used it to systematically beat Z at their own game.
It's a tragic arc. By 1976, just 3 years after the coffin tank was the most desired bike in America, Z motorcycles were suddenly a rare sight on starting lines. The sales just evaporated overnight as riders flocked to the lighter, faster Japanese bikes.
It was a very fast fall from grace.
And that slow fade continued for decades as the brand limped along under the constraints of the Eastern Bloc economy. Let's fast forward to 1993. The Iron Curtain has fallen, the global market is open again. Cagiva, the massive Italian motorcycle manufacturer, actually buys the motorcycle division of Z. They see the heritage, and they intend to inject millions in capital, build new proprietary bikes, and revive the Z name to its former glory. It sounds like the perfect rescue story.
It had immense potential, sure, but the timing was disastrous. Cagiva had expanded too quickly globally, and by 1997, the Italian parent company ran into severe financial difficulties. They were bleeding cash, and they had to amputate their acquisitions to survive. The joint venture failed, and that failure brought an official, unceremonious end to the OZ motorcycle brand. Production stopped, and the legendary winged arrow logo was retired from two wheels.
So, after surviving the collapse of a post-war arms market, surviving nationalization, and conquering the dirt tracks of the world, it ends in an Italian boardroom.
Yeah, anticlimactic, isn't it?
It really is. But what is truly incredible is that the factory itself, the physical buildings in Strakanishche, and the descendants of those original gunsmiths and bicycle builders didn't just roll over and die. True to their 1929 survival instinct, they simply pivoted again. They took their century of deep institutional knowledge of precision machining, and they started manufacturing highly complex car components, specifically turbochargers. And since 1999, they have been manufacturing heavy-duty Desta brand forklifts. They are still building heavy machinery.
Because a company's legacy isn't confined to a decal on a gas tank. The legacy of VZ is the physical reality of survival cast into steel. They survive by adapting their core competency precision metalwork to whatever the world demands of them. And beautifully, there's a modern footnote to this story.
Oh, right. The new scooter.
Yes. Since 2018, an independent company called Azetta Motors has been producing the Azetta 506. It is a fully modern, high-performance electric scooter that flawlessly revives that iconic, torpedo-like 1950s design. The aesthetic spirit of Strakonici is quite literally still rolling silently down the road.
So what does this all mean? It is a remarkable testament to the sheer force of Czech engineering. From the precise, lethal mechanisms of an automatic firearm to the massive, ear-splitting 13,500 RPM roar of a V4 on an Austrian Grand Prix track, to the rugged, invincible simplicity of a dirt bike dominating the ISDT. And now, to the meticulous hands of the preservationists today who ensure that this deep, complex history isn't lost to rust. To see exactly what it takes to resurrect a machine like the 1936 Z175, make sure you visit the BluewaterAutoRestoration.com website. You can see the preservation philosophy in action. And as a reminder, our podcasts are available on Spotify, YouTube, Apple Podcasts, or SoundCloud.
Before we sign off, I want to leave you with one final thought to mull over. When you look back at the entire century-long history of Z, a very clear pattern emerges. They never innovated when they were comfortable. They only created their greatest, most paradigm-shifting leaps forward when they were absolutely forced to.
It was the total collapse of their weapons contracts that forced them to master civilian bicycles. It was the severe austerity of the post-war economy that forced them to engineer the brilliant space-saving Azetta scooter. It was the desperate need to beat heavier, more powerful four-stroke engines on the dirt track that forced them to harness the invisible physics of sound waves with the expansion chamber. It really makes you wonder, in today's modern world of limitless data, endless corporate budgets, and supercomputer-aided design, are we actually missing out on the kind of raw, world-changing innovation that only ever comes when your back is truly against the wall?